All right, welcome to day 12. You've got a couple packet pages and one textbook problem to do for homework. So we want to find our domain, which is the overlap. So in number 1, all real numbers except 0. With the radical, we need t greater than or equal to 0, so the overlap of that would be t greater than 0. In 2, we need t to stay small. It's got to stay within -2 to 2 inclusive. The second one, we have all real numbers, so it's just t greater than or equal to -2, less than or equal to 2. In our domain of a log, the inside needs to be positive, so t has to be greater than 0. Our exponential is all real numbers, so we just get t greater than 0. And in 4, sign's good everywhere. The second one, we can't have plus and minus 1, so our domain would be all real numbers. T can't equal positive or -1. In 5, our magnitude. Do each of your parts squared. That ends up being 1, so we just get 1. And square each of our parts, take the square root, we get 5t. We have some limits here. As t approaches 0, sine t over t, we know that's just 1. In the second one, divide out a t, you have t minus 1, so when you do direct substitution of 0, you get -1 for the second part. In 8, as we go to infinity, that's an exponential decay function, so that will approach 0 as it flattens out. And in the second one, our exponent is greater in the denominator, so as t goes to infinity, the bottom will get much larger than the top, so that'll approach 0 as well. In 9, as t approaches 3, you can just do direct substitution in the first one to get 1/3. Second one, we can factor the numerator, divide out our t minus 3, then do direct substitution to get 6 for the second part. Continuous, similar idea to domain, the overlap of where they are continuous. So our first one is continuous when t is greater than or equal to 0. Second one, t is greater than or equal to 2, so the overlap of that would be when t is greater than or equal to 2. 11, sine and cos are both good everywhere. In 12, first part, all real numbers, it's continuous. Inverse sine is only continuous between t values of -1 and 1. Because remember, the t values in inverse sine are the same as the y values in regular sine, and those stay between -1 and 1. In 13, I wrote it with some intervals. So the first one, we basically can't have -1 and 1, so you could think of it as 3 intervals. That's the black there. Then the second one, similar idea, that's the green. So you could split that into 5 different intervals. Or you could just say all real numbers and t cannot equal plus and minus 3 and plus and minus 1. That would probably be the shorter way to write it. In 14, pick some both positive and negative values of t. You get some vectors to plot. Remember, those are like the tips of the vector that then create the vector valued function. And note the direction that it's going. Make sure you have arrows to represent that. In 15, pick your nice values for t. And notice we're going counterclockwise in that one. And that was it for the homework. We're going to do a whole bunch of different things with vector value functions today. So first off is derivatives. If you have some vector valued function there, r of t, the derivative r prime of t is just the derivative of the individual parts. So if we want to find r prime of 1, that means we got to take the derivative and then just sub in 1. So we're going to have r prime of t is equal to the vector valued function of derivative of e to the t, which is e to the t, and derivative of e to the 2t, which would be e to the 2t times 2, or in other words, 2e to the 2t. If we now want to evaluate that at 1, e to the first is just e, and then when we sub in 1 to the second part, we'll get 2e to the second. And what is this telling us? Well, at the value t equals 1, we would have the position here, or the point, it would be e comma e squared. So that's what this is here roughly, e comma e squared. So this velocity vector, if the original had been a position, this would be a velocity. What this is essentially saying is we would go e more to the right and 2e squared up. So maybe a vector kind of like that. So what it's telling you is it's telling you the direction, the speed, and the steepness at that point. If we move down to the bottom, we're going to do derivative at pi over 4. So r prime of t, derivative of sine is just cos t. Derivative of cos would be negative sine t. And at pi over 4, we know both sine and cos are just square root of 2 over 2. So we'll have square root of 2 over 2 positive for this one, negative square root of 2 over 2 for that one. So if we were to plot our velocity vector, so from the point on the function at pi over 4, we would go down square root of 2 over 2, and then, or sorry, we would go right square root of 2 over 2 and down square root of 2 over 2. So it would go right, and then it would go down. Now because this point on the circle here would happen to be square root of 2 comma square root of 2, it's actually going down to the x-axis. So our velocity vector would end up looking like this, because that would be down square root of 2 over 2 and also right square root of 2 over 2. And that's showing us at that instant the vector value function is going in that direction. That speed, okay, the length of the vector is telling us the speed there and the steepness of it. So if we flip over to the next page, a vector valued function is considered to be smooth if the first derivative, if the component parts are continuous, and at no time are they both 0. So if they are not simultaneously 0 at the same time. That's a little redundant. If they're not simultaneously 0. So let's take our derivative. We'll have to use a chain rule here. We'll have 3, sine will now be squared, and we got to multiply by the derivative of sine, which is cos t. So that would be our initial part for the first one. We'd have 3 cos squared t times a negative sine. So eventually that would be negative 3 cos squared t times sine, because we can just bring that negative out front. Well, sines and coses, those are continuous everywhere, so we don't have to worry about that part of it. But we've got to check and make sure they are not simultaneously 0 anywhere. Well, because both of them have sines and coses being multiplied, they're both going to be 0 anytime sine or cos is 0. So these are going to both be 0, or they're going to not be smooth at 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. So we've got to figure out a way to write that nicely to tell where it is smooth. So we can say it's smooth for all real numbers. Now, we could say that 0 is really 0 pi over 2. Then we have 1 pi over 2. Pi is really 2 pi over 2. So we could say all real numbers, but t cannot equal n pi over 2, where n is an integer. So that's how you determine where something's smooth. If we go down to the bottom, now we're going to look at definite integrals. When you do a definite integral, kind of like you just do the derivative of each of the parts, you'll do the integral of each of the component parts. So this is just going to be the integral from 1 to 4 of 3 square root of 2 dt, comma, the integral from 1 to 4 of 2t plus 1 dt. So we'll just find each of those, and that'll give us what our vector valued function would be for the integral. So this is t to the 1/2. So we're going to have t to the 3/2. When you divide 3/2 by 3, that's like multiplying by 2/3. So we'll just get 2 out front. And we'll have to evaluate that from 1 to 4. 2t plus 1 will have t squared plus t. And that's going to have to be evaluated from 1 to 4 as well. 4 to the 3/2, square root of 4 is 2. 2 to the 3rd is 8. 8 times 2 is 16. 1 raised to anything is 1, then times the 2 is 2, so we'll have 16 minus 2 there. When we sub in the 4, we'll have 16 plus 4, so 20. And then 1 plus 1 is 2, so we'll have minus 2. So we eventually get that this is just 14, 18. So if we think of an integral of like a basic function that we worked with early on, what that was telling us was the area between the graph and the x-axis on that interval. So what was that net change in that area? So let's think about what the definite integral of this vector valued function would give us. And if we go to the next page, we'll see that. So let's say r of t was our velocity function. If you're doing the integral from 1 to 4, which notice that matches with what we had here. So our integral from 1 to 4. So if we have that integral from 1 to 4, that's telling us our displacement in each of the directions. So the 14 is meaning we are 14 further to the right in the horizontal direction, and we are 18 further up in the vertical direction. If they were negatives, they would be left or down. If you want the overall displacement, you would then have to do the magnitude of that vector, the 14, 18. So if you were to do that, that would just be square root of 14 squared plus 18 squared. That would eventually give you square root of 520, which is the same as 2 square root of 130. So that would be your overall, think of it at like direct or as a crow flies displacement. The 14, 18 would be if you moved right then up, how your displacement would be. So down on the bottom we have, if we think of things as velocity and acceleration. So suppose r of t represents like our position function. That's the location of the object in our plane. So your velocity then is your first derivative. The speed is your magnitude calculation of the velocity vector. And then your acceleration is just the second derivative of that original. So nothing too earth-shattering there. And if we go to the next page, we're going to practice finding each of these things for some different questions. So we've got 3 sine t, 3 cos t. That's what it would look like if we subbed in things like 0, pi over 2, and all that. So we want to find the position at pi over 4. So we're just going to do r of pi over 4. Well, sine and cos of pi over 4 are just square root of 2 over 2. So we're going to get 3 square root of 2 over 2, and we'll get 3 square root of 2 over 2 for the second part as well. So that's going to be roughly right here is where we're working with. So part B now, we want to do our velocity vector at pi over 4. Well, look, first let's find what our velocity vector valued function is. Derivative of sine would be cos. Derivative of cos is negative sine. And then we're going to do this at pi over 4. Well, we've still got square root of 2 over 2, so this is going to be 3 square root of 2 over 2 again, and this will be minus 3 square root of 2 over 2. And what we're going to do is we're going to draw in that velocity vector. So from our point, we want to move right 3 square root of 2 over 2, and then we want to move down 3 square root of 2 over 2. Well, notice we can kind of get a sense of what 3 square root of 2 over 2 is based on where that point is. It's around like 2.1-ish or so. So we're going to move right that same amount and then down that same amount. So because it's down the same amount, it should end up on the x-axis. So this is our velocity vector right there. So for c, we want the speed. C is just the magnitude of our velocity vector. So we're going to have the square root of 3 radical 2 over 2 squared plus negative 3 radical 2 over 2 all squared. I should probably label this, so this is question C. And we're doing the magnitude of r prime pi over 4, which is the same as saying the speed. So if you square 3, you get a 9. Square a square root of 2, you get a 2. So that's 18. And then 2 squared is 4. So 18 over 4 is going to give us 9 halves for each of those. So that's going to be 18 halves, which is just 9, and square root of 9 is 3. So what that's telling us is basically the length of that vector is 3, which is the magnitude of it. And then the last one we want is the acceleration vector, which is our second derivative. So in our black there in B, we have 3 cos t, negative 3 sine t. So we're now going to have negative 3 sine t, comma, negative 3 cos t. And we want to evaluate that at pi over 4. Well, we still got square root of 2 over 2, so this is minus 3 square root of 2 over 2, minus 3 square root of 2 over 2. And when we plot that, we can do our down square root of 3 over 2 over 2 and left. So that's basically just going to take us back to here. So that's our acceleration vector. And what the acceleration vector is, you can see right there, it is the pole of the object. So basically, where from that instant, the pole is going to lead it, and by pole, P-U-L-L, not P-O-L-E, where it's going to lead it to its next spot. So it's being pulled towards the center, so that's why it creates that circular form. And something that just pops into my head right now is think about like planetary motion. Okay, the sun helps keep things in their orbits because of that pole of it as well. So if we look down to the bottom, we'll do the same thing, but for this new vector valued function. And because you already have the notes, it's kind of a spoiler alert already of what the graph looks like. So there's our original path. And we want to find at t equals 1. Well, let's see at r of 1 where we would be located. E to the first is just e, and natural log of 1 is 0. So that's going to be our x-intercept there. That's where we're working with. So we want to find the velocity and acceleration and speed at t equals 1. So let's start with r prime of t. That would be e of t, comma 1 over t. We'll do r prime of 1. That's going to be e, comma 1. So E is like 2.7, so this means we want to go 2.7 to the right and 1 up. So we're already at 2.7-ish, so we should be about 5.4. And then up 1, so that's about there. So that would be our velocity vector. Well, let's do our speed. So that's going to be the square root of e squared plus 1 squared. And that's not going to come out nice, but to 3 decimal places, that's 2.896. And then our acceleration, we'll get e to the t again. 1 over t is like t to the negative 1, so negative 1 multiplies out front. We now have t to the negative 2, so that's negative 1 over t squared. And when we do that acceleration at 1, we'll get e again, but this time we'll get negative 1. So from our original point to mark our acceleration, we have to go right E again, but this time down 1. So that would be about here. So again, that's the pull. That's where we're being pulled, the object at that instant. All right, if we go to the next page, so we've got a particle that's starting from rest from -1, 3. So this is our position function, or our position vector valued function. So let's think of that as like s of t. If we're starting, or I should say s of 0, because it's where we're starting, our initial velocity vectored value function would be 0, 0, because we're starting from rest, and we have our acceleration. So if you start with acceleration, to get the velocity, we would want to do the antiderivative. Antiderivative of 1 is t plus c, and we're going to call it c1 because we have two constants. Antiderivative of 2 is 2t plus c2. Well, now we'll work with our initial velocity. We know v0 has to be 0, 0. So t plus, sorry, we should have 0 plus c1 should equal 0. So c1 is 0. And 2 times 0 plus c2 should equal 0. And that's coming from subbing in the 0 in for t, and then setting them each equal to 0, because that was our function. If this was v of 1 equals 3, 4, then we would have done 1 subbed in for t, and it would equal 3, 1 subbed in for t, and it would equal 4. So our velocity then is just t, 2t after we resolve our constants. For our position function, we'll do an antiderivative again. We'll have 1/2 t squared, and I'm going to use a different constant. We'll call it d1. And then we're going to have t squared plus d2. Well, our starting position is -1, 3. So when we do 1/2 times 0 squared plus d1, it should equal -1. So d1 is just -1. When we do 0 squared plus d2, it should equal 3. So d2 is just 3. So that means our position function with our constants resolved is 1/2 t squared minus 1 and t squared plus 3. And now we're ready to answer the question. We want to know the position of the particle after 2 seconds. So we'll just do s of 2. And we'll fill in 2 for all the t's. So we'll have 4 times 1/2, which is 2, minus 1, which is 1. 2 squared is 4, plus 3 is 7. So after 2 seconds, we are located at 1, 7. And then we're going to skip the one that is at the bottom of that page. So you've got your day 12 homework to be working on. Keep in mind your test is coming up Friday, so you could be working on the review sheet as well. Have a great rest of your day.